So the next speaker is Fedor Popov, who was a graduate student here, and we're happy to have him back. Supersymmetric QCD models in 2D.
Okay. First of all, I would like to thank organizers for this wonderful workshop here at Princeton and the Wonder Flatiron Institute. I've learned a lot of interesting topics and learned a lot of other stuff. And second of all, I'm grateful for the opportunity to speak about my recent work and some work in progress. That is devoted to the study of supersymmetric QCD models in two dimensions. So I will try to explain to you why these QCD models, supersymmetric models, are different from the high-dimensional cousins. I will try to persuade you that it's indeed different. I will provide some evidence for that and some simple explanations why it happens. And if you have any questions during my talk, please interrupt me and I will try to answer. So let me start with the motivation. In case you forgot, we want to study quantum chromodynamics. The Lagrangian is here, it's quite simple, but at low energies it becomes strongly coupled and we don't know how to solve it. There is a lot of interesting ideas, and we have heard talks about these ideas how to solve these models in low energies, include just putting the theory on a lattice or study large n limit and hope that maybe we have some collective behaviors there. And maybe we can construct some sort of effective string theory description of this model. But right now I want to concentrate by studying this model in 2D. In 2D, we still have non-trivial Young-Mills interaction coming here, but we have non-propagating degrees of freedom. That gauge degrees of freedom becomes non-propagating because of in 2 dimensions vector particle has d minus 2 zero propagating degrees of freedom. Therefore, this model would be still have some interesting impact of this term, but maybe it will be easy to solve. And for instance, indeed, Tufte managed to show that if you consider such a model with quarks in the fundamental representation in 2D, then in the Lagrangian limit you can write down a whole set of equations that describe the eigenstate and eigenenergies of this model. So for that, let me briefly explain how it works. You introduce light cone coordinates like this one, as we do usually in 2D. In this case, Lorentz group acts diagonally in these coordinates. And we introduce light cone gauge. We set one of the components of the vector field to be equal to 0. It gives you two things. First of all, Fedor-Popov determinant becomes trivial here, so we don't have to deal with gauss. We make the Young-Mills term completely quadratic, like this one, and it doesn't contain time derivatives. And the only non-trivial thing comes from this term that is responsible for interaction between quark current and the gauge fields. And thanks to some algebra of the gamma matrix system of dimensions and the Lagrangian limit, we can completely find what the diagrams contribute in the Lagrangian limit, namely this one, like this one. And we can write down the closed form of Dyson-Schwinger equation for the quark propagator and for the meson states, like this one, and completely solve it. So you see it's already a big progress in comparison to 4D, where we can write down some sort of closed equations for this one. But this model misses one important piece, namely some adjoint degrees of freedom that present in higher dimensions. So we want to model this adjoint degrees of freedom by adding some adjoint matter. And for simplicity, I will add only the Majorana fermions in the adjoint representation like this one. And they will graph speaking model gauge degrees of freedom in higher dimensions. One can notice that in this case, Tufte solution doesn't work because of now we have infinitely many more diagrams here. So we have to come up with some other ways to solve this theory. And for that, we use light cone quantization. So we start with the following action like this one. Here, psi is the Majorana fermions in the adjoint representations, and V are some other massless fermions in various representations. I introduce them to make life much more interesting, and I will explain later what the effects they have on this model. After that, you can introduce light cone gauge. You set one of these components to be equal to 0, integrate out A minus and psi minus, and get the following simple action here. And now we can treat this as a usual, and we forgot that it's like our special component now is, and if we treat now the x plus or x minus component as a special component, we can say that it's just a simple model describing propagating fermions that have very strange kinetic term and this interaction. So this term is just like usual zero action for non-interacting and non-propagating fermions in one dimension. This term gives you kinetic energy for the fermions and has very simple meaning. In these coordinates, the energy is related to momentum by the relation n squared over 2p. And we have this interaction. It comes from integrating out a minus. It becomes instantaneous and just gives you interaction between currents. And from that you see that we immediately have perturbative confinement, because of when I invert this operator, I will get just linear potential between these currents. Like that. But now let me try to somehow put it in a computer and find the spectrum of this model. For that, I can just introduce the following anti-commutation relation, like this one and this one. I do the Fourier transformation. So I introduce this operator psi k and ck b minus k. And since they satisfy usual anti-commutation relation, I can build usual Fock space. For that, let me find the vacuum state. The vacuum state will be the one that annihilated by all operators with negative k plus. So Hilbert space consists of only the fermions that propagate forward in time, and all the states could be constructed by acting with these operators on this vacuum. So we construct all of these possible words with all of these possible k1 plus and k2 plus, and it will give us all states. Also using the Lorentz symmetry, I can set the sum of these k pluses to be equal to 1 and study only this particular sector. But even more, we can now use the leftover gauge transformations to see that we have leftover gauge transformation, first of all, because of if I set a plus to 0, I can make a gauge transformation that does not depend on special coordinate x plus, and it will keep my gauge the same. So we need to get rid of this leftover gauge transformation that acts like a global just like a global symmetry in this Hilbert space. And by considering, taking into account these transformations, we concentrated on the gauge singlet of this Hilbert space. We can notice that Hamiltonian and momentum acts properly on this subspace, that the map singlets back to singlets. And this term acts nicely in this space because of singlets, they are annihilated by current at zero momentum, so it term doesn't bring any troubles to us. And now we can study this model, construct this all Hilbert spaces, construct this Hamiltonian, study the properties of the spectrum as a function of this parameter, mass of the adjoint fermion. It was done in this paper by Ross Dempsey, Igor Klibanov, Silvia Puffi, and Lokilin. And you see that in some specific point, we see that the first bosonic state intersects with the first fermionic state. It's not something, at first it seems it's not something special, because of these two curves belong to two different symmetry sectors. One is described by fermionic degrees of freedom, the other one bosonic degrees of freedom. Hence, we expect that at some point they should intersect, and therefore it seems that it's just some coincidence. But if you study much more high excited states, you will see that they all have a crossing at this particular point. So for each bosonic state you have a fermionic one, and for each fermionic one you have bosonic one. Okay, so it seems that we have a supersymmetry at this point. Let us try to construct a generator, supercharge of this symmetry. That was first done by David Kutasov. And actually, first David Kutasov introduced the supersymmetry, and after that it was checked numerically. So to construct the supersymmetry charge, we need to have a fermionic operator, so it should consist of odd number of fermions. It should be a gauge singlet, so we know how to contract now the indices here. And it should have the correct dimension. So we know what how to put correctly the dependence on momentum. After that, we can try the most simplest supercharge, like this one, and check that indeed if I take a square of this supercharge, I get back my Hamiltonian like this one, but it sets this mass of this adjoint fermion to some specific value equal to this thing. And since it's Hamiltonian the square of this operator, we necessarily get that P minus compute with Q minus, so it's a symmetry. And since this consists of odd number of fermions, it maps fermions to bosons. So it precisely explains this degeneracy at this specific point. So we understood it from like this complicating light quantization. Let us try to find out what happened in the first place, not going to the light quantization. For that, let us try to find the most simplest model where that things occurs. And for that, let me consider supersymmetric Schwinger model. So we have here fermions, massive fermions in the adjoint representation of U1, so they don't have any charge Q. We have U1 gauge field here, and I couple to this U1 gauge field some bunch of massless fermions with various charged Qi's here. This model is quite simple.
Excuse me, what's the you denote charged fermions and zero charged fermions, but one and the same letter?
One
Is
has
it
index.
true?
Is it index I?
Okay,
I wanted
thank
to
you.
make them all equal, but some is more equal than the others. Yes. Okay, so we can completely solve this part of this model. Namely, just describes n minus 1 massless fermions with zero charge, so we can forget completely about them. And one massive scalar bosonic degrees of freedom with the following mass. It's a famous Schwinger solution. And by adjusting the mass of the adjoint fermion to this particular value, we get the supersymmetry for free here. Roughly speaking, it comes just from coupling non-interacting system with another non-interacting system.
But this scalar, has no partner, right?
No, it has partner. I just introduced this.
Scalar is 1 and fermion is n, right?
No, scalar is 1. Fermion is also 1. Is just.
So for each I?
No. You just you can solve this model via bosonization, and you see that collectively this massless fermion just gives the mass to the gauge boson.
Yeah.
Here, and after that you have n minus 1 massless fermions that completely decouple from the rest of the system, and I can just forget them, put them under the rug.
I see. So in this way, massive particle is just like an analog of massive photon, and it's just one, right?
Yes, just one. And n minus 1 massless fermions I kind of forget.
But then this Q generator connects. So it means that for massive one it's a singlet, right? And other one move between themselves.
Yes.
I see.
Okay.
Isn't it a little strange that adding just three non-interacting particles, totally irrelevant to any interactions, you establish some kind of supersymmetry which seems a little weird, right?
No, is that what?
Because photon, in a sense, it does interact. Okay, it may be some kind of artificial low energy supersymmetry.
You can mix fermion with the state which is two fermions. So in this way, it is supersymmetry between, just written in terms of fermions, but you can say that other two fermions is like a spin zero.
Wow.
Yeah.
Yes. Okay. So this, yes?
Is it important that n is greater than 1 here?
No, you can set just n is equal to 1. That's all. I just wanted, because of this kind of effect you can observe in QCD, that it will shift your supersymmetric mass also. Here.
Yeah, so
Yes.
this is not like, there is a supersymmetric sector, but the whole thing is not supersymmetric, right?
Yes,
It's a fermion
yes,
field.
yes. But
So
like,
you don't expect
yeah, so I'm
anything.
speaking this, there is some sector that has supersymmetry and some non-interacting sector that completely decouple from the rest of the system. And we will observe the same situation also in QCD. Okay, so we expect to see supersymmetry here, and because of this model is very simple, we can find out what's happening here. For that, let me rewrite a little bit this model. So I want to rewrite this model as some CFT plus some relevant perturbation. For that, I will decompose my vector field in the following way, just Hodge decomposition. We can completely forget about this gauge transformation here, because we have gauge theory. We have this term. It could be removed. The only interaction comes from the massless fermions, but it could be removed by this gamma 5 transformation here. But the price that we pay is that we introduce this additional term into the action, like this one. And after that, I can represent this original action the following way. I have just like a supersymmetric U1 Wiener-Witten model at level K. So we have a massless fermion and compact scalar, like this one. And after that, when I introduce mass and remove action, it just I can observe it as a deformation by this relevant perturbation. So we have deformation of free CFT, U1 supersymmetric Wiener-Witten by relevant operator. This guy has supersymmetry at any level K. And now if we demand that our perturbation respects the supersymmetry, we will see that it sets mass to some particular value determined by this relation. So let us try to apply the same strategy for the QCD here. So let me rewrite this QCD action as a perturbation of some CFT by some relevant perturbation. For that, again, I will use the light cone gauge. I will set a minus to 0, parameterize a plus in the following way. After that, I plug it back into this action and rotate away this G from my fermions, massless fermions, and it will give me the following action, like this one. This part easily recognizes as supersymmetric Wiener-Witten model at level K, and this is some deformation of this model. Okay, Wiener-Witten model has. Okay, sorry. Wiener-Witten model has supersymmetry. You can write down it like that. Here I forgot to put 1 over K. Here. After that, one can see that if I look at the Hilbert space of this Wiener-Witten model, I will see that it coincides with the Hilbert space of states that I wrote in the light cone quantization. Namely, we have again operators psi n, psi m, operators j, a, n, okay, like this one. We have a state. Vacuum state is annihilated by all operators with negative momentum here for n less than equal. And our DLCQ Hamiltonian is just this Hamiltonian here that acts in the following Hilbert space. So in some sense, DLCQ is just in some sense Hamiltonian truncation that was introduced by the Molotchikov for Wiener-Witten model, but the Hamiltonian has the following form. Here. And by taking the limit of large dimension, we should reproduce the results of the LCQ. So from that, we see that in light cone quantization, we secretly have already the Hilbert space of Wiener-Witten model, okay. So it has this super symmetry. And now let us try to write some perturbation of this model such that it will respect this corresponding supersymmetry. The deformation coming from this QCD Lagrangian has the following form, and if we demand that it's invariant under the action of the supersymmetry, one can see that we have to set the mass of a joint fermion to this particular value here, and we can find that supersymmetry has the following form here. After that, you see interesting fact that now in comparison to the previous result, we have dependence on the level K here, and because of this level K comes from not only from adjoint fermions but various other massless components, we can set this k to be any value. And this extends the results that we've known before, because now we can construct a supersymmetric point for any other models by adding these massless fermions. And you can ask Ross to diagonalize this Hamiltonian, and he will be very happy to do that. So, for instance, you can add massless fermions in the adjoint representation. For instance, you can add additional 1 or 2 1 and see that indeed we have again a supersymmetric point, but it gets shifted precisely by this formula. Okay. So, but let us come back to the classical Lagrangian and see where it fails at quantum level. So we have the supersymmetry transformations in 2D that maps psi to gauge bosons and gauge bosons to psi. And if we stare at the action long enough, we will see that we have the following problematic term coming from the interaction between gauge bosons and the fermion current. And we will see how it changes under the action of supersymmetry. In quantum level, it acquires some additional piece that looks like this one, plus some classical piece here. And in order to compensate this transformation, we must introduce into the action this term. This, as it was pointed out by my colleague from Simon Center, Justin Kalt, which is just a Canisian anomaly in 2D. We know that in 4D we have Canisian anomaly. Sometimes composite operators acquire some quantum corrections under the action of supersymmetry, and we should take into account. But here, this correction already arises at the level of action, and we should take this into account here. So we add the following compensating term and get supersymmetry here. So it brings me to the end of my talk. So there is some outlook and conclusion. So first of all, can we now extend to some other supersymmetric models? For instance, can we construct an equal to supersymmetric QCD? Here, one of the ways of doing that, we can just consider this picture and notice that sometimes this Gauss-Levy model has an equal to supersymmetry. Namely, when, because we just nonlinear sigma model on a group manifold, we know that from the works by Luis Alvarez-Gamay and other people from Stony Brook, that if the target manifold has a complex structure, then we can construct an equal to supercharge, and hence maybe this supercharge will be also be respected by this deformation. But if you look carefully at this additional supersymmetric transformations, you will find out that it does not respect gauge group, and hence it will not act properly on this additional term. The other way is to say that let us start with some operator Q. It was introduced in this approach known as supersymmetric DLCQ. So just that was introduced by Oleg Lunin and his collaborators. So you should just introduce some operator Q, take a square, and declare that it's your Hamiltonian. So it would be nice to connect to some other well-known QCD models, what these models correspond to its usual level, and maybe understand how maybe we can introduce as a chiral n equal 1 method. And the other interesting question, maybe at this specific point, we see that we have additional conserved charge. Maybe at this specific point, we can have whole hierarchy additional charges, and that makes the system actually integrable. Okay, so thank you for your attention.
I just want to make a remark about your singular use of supersymmetric points.
Yes.
I think in pure QCD adjoint,
Yes.
this is one of the two special points. In massless QCD adjoint,
Yes.
okay, you only have Majorana fermions and gauge fields. The theory also has exact spectral degeneracy between bosons and fermions. This is pointed out by me, Alexei Cherman, and Zaki, as well as by Jome Gomez. So pure QCD adjoint in 2D massless point also has exact spectral degeneracy. If you look to graded partition function, graded by -1 to f, it is exactly 0 actually. So,
but this maps between different sectors, right?
Yeah, it maps different universes. If supersymmetry doesn't change the universe.
sure.
That's not a supersymmetry, it's some kind of other symmetry.
Yeah, it is, but it's an exact spectral degeneracy. Yes, it is implied by some mixed anomaly involving fermion number modulo 2, but also that's what, well, you know, Shonegomi and his friends point out.
I just wanted to make a comment about, like there seem to be two different types of models. One with this extra gapless stuff that's not obviously supersymmetric, but it might be just. But then there are models which don't have extra gapless stuff. And for example, if you take one massive adjoint and one massless adjoint, that's a gapless model with exact supersymmetry at m squared equals 2g squared n over pi.
Like it was, like you can see here, that you completely remove this massless sector here.
Yeah, but so there are models which are very similar to the just usual adjoint QCD, but I guess the question is, can the models with extra gapless stuff also be made supersymmetric? And
if like this massless sector could be
that it can flow to a CFT.
Yeah, I had one question about the Schwinger model.
Yes.
So is there a way to retain supersymmetry at non-zero electron mass?
What do you mean? That I introduced.
You add an electron mass. Let's
Yes,
say n equals. Let's say
This is the neutral.
Let's say n equals 1. Let's say n equals 1. You add electron mass.
Yes, I have.
Is there a way to couple the adjoint to the rest with some vortex to retain supersymmetry?
I have not thought about that, but maybe it could be done. But I don't think that it will be supersymmetric at this point.
Or it would have to be some kind of sine Gordon, or it's more complicated.
Yeah, it's more complicated. Here, just very simple to see. But maybe you needed some like parameter space to again.
Yeah, because you have lots of additional couplings to it. Right.
So maybe.
No, it may be just misses, but I wonder, you have this Hoft model, and there was spectrum, he calculated particular features like, say, P and something as analog of pi, and you know, so you have the, I wonder, no, now you have this kind of analog of this with adjoint, right? And what is this special feature, you know, which differentiates this adjoint spectrum from, from this when it was fundamental, right? When fermions were there.
Yeah, now you can roughly, in the case when you have TOOF model with only fundamentals, you can construct the N-Largen limit. You have, you can write down immediately the eigen states for this model. It just contains two fermions there. Here, because you have adjoint matter, you can add a lot of psi's between this. Between them, you can, for instance, construct states like trace psi to some power n, and so on. And now this interaction will mix this different.
So it could be more than two, right? And it's
more than two, yes. And it drastically complicates the analysis of this model.
Yeah, it's a non-trivial theory of closed strings with a lot of bits in the.
Zohar, why do you say they are different universes? They are not. You can construct both bosons and fermions on the same vacuum.
They are.
Because time reversals changes the analysis by n/2. So
It is a mixed anomaly between fermion number and chiral symmetry.
Yeah, so it changes the universe by n/2 units.
Maybe. But
No,
it doesn't
it's
mean-
just, look, we've done the numerics. You can't argue with the computer.
I don't think I agree with that.
But you don't see supersymmetry. Anyways, there will be another talk on exactly these questions, so maybe we should thank Fedor.